Alrighty, guys. So today's lesson, we are going to focus on how to apply the rules we've been learning about the mole to now volume. Alright, so this is one of the properties that we measure when looking at the physical properties of elements, the volume. Now, we've already learned how to use the mole to determine the mass of a given compound and an element. So we're going to skip that section and we're going to go directly to the volume. All right, remember, we can use the moles given of a compound or even an atom to determine the mass in grams and vice versa. Now we're going to use the moles of a compound or an atom to determine its volume, or use the volume to determine the moles. All right, so let's get forward. All right, so the first thing that we first have to understand, all right, is something called Avogadro's hypothesis. All right, Avogadro's hypothesis states that an equal volume of gases at the same temperature and pressure contain equal numbers of particles. That means if I have 5 liters of oxygen present and I also have 5 liters of nitrogen present, and they're both taken at the same temperature and at the same pressure, they're going to have the same amount of particles. All right, we're going to have, let's say, I don't know, 10.1 times 10 to the 26 particles of nitrogen and 10.1 times 10 to the 6 particles of oxygen. All right, anytime that you have an equal volume of two gases and they're taken at the same temperature and the pressure, we're going to have the equal amount of particles between those two compounds or atoms. All right, in my case, it was atoms because we were talking about nitrogen and oxygen. Now, even though the particles that make up different gases are not the same size, all right, we know based off of periodic trends that elements that are farthest to the left and to the bottom are going to be larger in size. Well, even if we're talking about two atoms that have different sizes, they're still going to follow this hypothesis. All right, as long as they have the same volume and the same temperature and pressure, they're going to have equal amounts of particles. All right. And those are two examples. All right, you can think of, I don't know, we can think of this as barium, and then this one is francium. All right, these obviously are larger, but because they're in the same exact volume, taken at the same temperature and pressure, we're going to have the same amount of particles as we do to the right as we do to the left. All right. So, because the volume of a gas varies with a change in temperature or a change in pressure, we measure the volume of a gas at a standard temperature and pressure. And all that means is anytime that we are considering the volume of a gas, there are two things that can change the volume of a gas. If you change the temperature, you're going to change the volume. If you change the pressure, you're going to change the volume. So in order to prevent any changes or any undesired changes in our volume, we're going to keep the temperature standard and we're going to keep the pressure standard. We're going to keep those two things constant. All right, so the values are the following. We call those standard temperature and pressure, also known as STP. Anytime that you see that term STP, we're talking about a standard temperature and a standard pressure, something that we can all agree on, and those numbers remain constant so that our volume stays constant. The standard temperature is 0 degrees Celsius, which is also converted to 273 Kelvin. All right, we're going to start using Kelvin from here on. Kelvin is a new unit when measuring the amount of temperature, all right, Kelvin. And then the standard pressure is 1 atm or 1 atmosphere, all right. So at STP, at standard temperature pressure, we have 1 mole of any gas, and that takes on the volume of 22.4 liters. All right, anytime that a gas is at STP, anytime that a gas is at standard temperature and standard pressure, we're going to always have that same exact volume, 22.4 liters. I remember Avogadro's hypothesis says that if the temperature and the pressure remain the same, then we're always going to have the same volume. In this case, we call this the molar volume. The molar volume is always going to be 22.4 liters at STP. Take it a little farther. All right. Now, from here on, we're going to start trying to calculate the volume and the moles of a gas at STP. All right, so we're going to start using the molar volume, which again is 22.4 liters, and we're going to use it to convert the number of moles of gas and the volume of the gas at STP. All right, so that brings forth a new equality. 22.4 liters equals 1 mole at STP. Remember, at STP, 1 mole is going to have or take the space or occupy 22.4 liters. All right, and we can have the new conversion factor, 22.4 liters over 1 mole, and the reciprocal 1 mole over 22.4 liters. All right, all this is saying is that anytime that we have 1 mole that is currently under the conditions of standard temperature, standard pressure, STP, we're going to have that volume 22.4 liters. All right, let's do one example. Sorry. Just get rid of these. Sorry, I forgot to erase my answer. These answers should be fair, or these questions should be pretty easy, especially since we've been practicing how to convert moles and grams from one another. All right. All right, so the question is this. Sulfur dioxide, SO2, is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain, which is pretty cool. Determine the volume in liters of 0.6 moles SO2 gas at STP. All right. We're going to just, tackle these problems as we're used to. First and foremost, we're going to realize what we're given. All right. We are given first that we have 0.6 moles of sulfur dioxide. That's what's given. That's how many moles we're given. The next thing that we're given is that we're at STP. All right. At STP. Because we're at STP, that means we have a temperature of 273 Kelvin and we have a pressure of 1 atm. And because we're at STP, that means our volume is going to be 22.4 liters. 22.4 liters. All right, we're at STP, means all of these characteristics are acquainted with our sulfur dioxide. Now, step 2 is now we want to realize, okay, well, what are we solving for? All right, we want to determine the volume in liters. All right, we know we want liters at the end. All right, since we're at STP, we're going to use this volume to do the following. 0.6 moles. And remember that (22.4 liters equals 1 mole. So we're going to use that. 22.4 liters divided by 1 mole. Moles cancel out. 0.60 times 22. I think I still have the answer. 13.44. 13.44 liters of SO2. That is our answer. Very, very simple stuff. All right, we have 13.44 liters of SO2 at STP. All right, notice that, again, we obviously at 1 mole, our volume is 22.4 liters, but in this case, we're dealing with 0.60 moles. All right, that's not 1 mole. All right, that's 60% of 1 mole. That means we're going to have to use this as a conversion factor to convert our moles into liters using our STP value. All right, to get 13.44. All right, not bad at all. Very, very simple stuff. The toughest thing is just understanding the concepts and the theory behind it. All right, that is all for today's video. And yeah, peace. I will keep you guys updated on any changes. Alrighty, guys. Enjoy your Friday. Bye.